Welcome to the Deep Dive, your shortcut to being well-informed on, well, truly groundbreaking ideas. Today, we're jumping right into one of mathematics' most persistent challenges. We're talking about finding exact solutions for really complex polynomial equations. And we're going to unpack a fascinating new mathematical breakthrough that might just redefine how we tackle these things. The topic is Ezouidi's theorem, this deep dive. It's all about giving you the essential insights into a potentially major advance. Could really shift things in science and engineering.
Exactly. And our mission here is to explore how Ezouidi's theorem actually does it, how it gets these exact symbolic solutions for polynomials that have been, frankly, incredibly tough. Even for supercomputers, we'll use a specific example, a 14th degree polynomial, to really see the theorem in action, understand its novel approach.
Okay, let's set the scene. The problem. High-degree polynomial
Incredibly
equations.
tough. Even
They've
for
always been this
supercomputers,
huge
we'll use a
hurdle, right?
specific example,
So
a
to give you a
14th degree
feel for what we
polynomial,
mean,
to really
here's the
see the
polynomial from the source material. High-degree polynomial
incredibly tough. Even for
always minus
supercomputers,
14
we'll use a
next to
specific
13.
example,
So
a
to give you a
14th
feel
degree
for what we
polynomial, to
mean,
really
I
see
mean, it
that.
keeps going down to the constant term. It's a
polynomial.
monster, a 14th degree equation.
It definitely looks intimidating, and the real challenge of that kind of complexity comes down to the limits of, well, the methods we've always used. Think about classical approaches like numerical methods. Newton's method, for instance, they give estimates, pretty good estimates sometimes.
But estimates aren't always enough, are they?
Exactly. They come with this inherent risk of rounding errors. They just can't promise exact values. And that leads to a big question in many fields. What if you absolutely need perfect precision?
Right, and this is where things get really interesting historically. For centuries, mathematicians wrestled with this. We even have Abel's theorem,
Ah, yes, Abel's impossibility theorem.
which basically states that certain polynomials, specifically those of degree 5 or higher, generally can't be solved using radicals. You know, simple roots like square roots, cube roots, and basic arithmetic.
And that theorem has been a cornerstone, a fundamental barrier in algebra for a long, long time.
So it seems like we hit a wall.
Well, that's where Ezouidi's theorem comes in, offering a completely different angle. While traditional methods hit that wall, or get limited by Abel's theorem for radical solutions, Ezouidi's theorem claims it can find exact symbolic roots. It doesn't actually contradict Abel's theorem, which is about solutions in radicals. Ezouidi's method finds exact solutions, sometimes involving things like complex exponentials, by revealing a sort of hidden algebraic structure that lets us factor these complex beasts in a new way.
So it's not just approximating, it's finding the actual answer.
Precisely. It claims to deliver the exact solvable roots for equations we might have thought were effectively unsolvable in closed form. A fundamental shift.
Okay, so Ezouidi's theorem is positioned as this promising alternative. A systematic process that gets around the old roadblocks of classical algebra and numerical methods. It sounds, well, almost too good to be true. What's the core idea? How does it work?
Well, the core methodology is quite elegant, actually. The theorem lets us break down the polynomial piece by piece and solve for the roots symbolically. It uses a recursive process.
Recursive, meaning it refers back to itself somehow.
Exactly. Think of it like building something complex, but each step depends logically on the previous one. Here, we're systematically calculating symbolic coefficients. Each calculation refines our picture of the polynomial structure. It keeps going until the polynomial is broken down into its simplest solvable components. And because it's all symbolic, we avoid those approximation errors entirely. We get the exact values.
And you mentioned our specific 14th degree example. The source notes something interesting. x1 is a root, and it appears twice, a root of multiplicity 2. How does the theorem account for that?
That's handled within the recursive process itself. The method starts by representing the polynomial using these symbolic coefficients instead of the huge numbers we saw earlier. The calculation of these coefficients is key. The formula, conceptually, uses things like binomial coefficients, terms that adjust the degree, base coefficients, and crucially, it references earlier terms in the polynomial as it calculates later ones. It's this recursive referencing that ensures we're always working with precise symbolic values, not numerical estimates.
Okay, and for this specific 14th degree polynomial, what did this process reveal? What did those symbolic coefficients look like?
This is where it gets quite neat. For this particular polynomial, the calculations show that most of those symbolic coefficients, they actually turn out to be 0. S0R, S2R, S1R, S2R, all the way up to S5R, then S7R through S12R, all 0.
Wow, okay, so only a few are left.
2, in fact. The non-zero ones are S6 more, which calculates to negatively 3,000 times 14 to the power of 7, and 13R, which is 5,000 times 14 to the power of 14.
So wait, that incredibly complicated 14th degree polynomial we started with, it simplifies.
Dramatically, because all those other coefficients are 0, the polynomial boils down to a much, much simpler form. Px by 14 minus S6R times by 7 plus S13R equals 0.
Hold on, x to the 14 by x to the 7. That looks almost like a quadratic equation, doesn't it? If you think of part 7 as the variable.
Exactly. You can rewrite it precisely like that. Let y equals like 7. Then the equation becomes y squared minus S6R times y plus S13R equals 0. Or plugging the values back in, by 7, 2 plus 3,547 times by 7 plus 5,000 times 14 equals 0.
That's a huge simplification from that incredibly long initial form.
It really is. And from this much simpler equation, which is essentially quadratic and by 7, we can derive the exact roots. These roots are expressed using complex exponentials. Expressions involving e's are raised to some power, often involving I, the imaginary unit. They capture all the roots, including the complex ones, with perfect precision.
No approximations at all.
None. It's a direct result of the recursive symbolic process. Precise solvable roots.
So let's connect the dots. The big takeaway here, the fundamental difference, is Ezouidi's theorem gives precise, formula-based symbolic solutions, not just estimates.
That's the core claim. Exact answers, completely free from rounding errors.
And can you check them?
Absolutely. That's crucial. You take these exact symbolic roots, plug them back into the original full 14th degree polynomial equation, px, and it should equal 0 perfectly. This can be verified using symbolic computation software, confirming the precision. It really works out.
Okay, and here's maybe the most compelling part for you listening.
Yeah.
The claim is this method isn't just for this one example. It can be applied to any high-degree polynomial.
That is the assertion, yes.
Yeah.
It's presented as a general method.
Which, if true, is, well, it's a massive shift in how we think about solving these equations. It really makes you reconsider what's possible, doesn't it?
It certainly does. And thinking about the bigger picture, this could be incredibly useful. Think about fields like physics, engineering, computer science, areas where precision is paramount.
Right, where approximations might not cut it.
Exactly. In those fields, exact symbolic solutions aren't just, mathematically elegant. They're often crucial for model accuracy, for simulations, for design. Imagine designing complex systems, say, in control theory or quantum mechanics. Even tiny numerical errors in those cases can lead to significant deviations or instability down the line. Having exact solutions avoids that completely. So yes, it represents potentially a major step forward, maybe unlocking solutions or levels of precision we thought were out of reach.
So wrapping up this deep dive, we've explored how Ezouidi's theorem aims to break through those long-standing limitations, how it offers a path to exact symbolic solutions for these really complex, high-degree polynomials.
And maybe a final thought to leave you with. Just consider the implications. What happens when we can get perfect, mathematically exact answers in fields where, historically, we've had to rely on approximations? Think about science engineering, where even the tiniest error can cascade. What new discoveries, what new technologies might become possible when we're no longer limited by that numerical imprecision? It really opens up some fascinating possibilities to ponder.